Dovolte mi, abych vás přivítal na první přednášce série přednášek, série nějakých významných přednášek, které pořádá Regionální centrum pokročilých technologií a materiálů. Na dnešním první přednášce budeme mít tu možnost, tu čest vyslechnout si přednášku pana profesora Josefa Michla z Univerzity v Coloradu. Já bych na úvod poprosil kolegu Radka Zbořila o kratičké představení pana profesora.
Dobrý den, vážený pane rektore, vážené dámy a pánové, milí hosté. Je mi ctí uvítat na půdě Univerzity Palackého a krátce představit životní dráhu profesora Josefa Michla, jednoho z nejvýznamnějších chemiků současnosti a editora jednoho z nejprestižnějších světových časopisů Chemical Reviews. Josef Michl se narodil v roce 1939 v Praze, doktorské studium ukončil v roce 1965 pod vedením profesora Rudolfa Zahradníka. Československo opustil v revolučním roce 1968. Postdoktorská léta strávil na University of Houston, University of Texas at Austin, Aarhus University v Dánsku a University of Utah, kde působil a získal profesoru v roce 1975. V letech 1986 až 1990 působil na University of Texas a následně ho profesní kroky přivedly na University of Colorado, kde působí až dosud na oddělení chemie a biochemie. Profesor Michl je hostujícím profesorem na desítkách zahraničních univerzit, editorem časopisu Chemical Reviews je od roku 1984. Je především jeho zásluhou, že Chemical Reviews má dnes vyšší impaktní faktor než nejznámější světové časopisy, jako je Nature nebo Science. A byl to právě profesor Michl, kdo zavedl tradici thematic issues, která se setkala s obrovským ohlasem odborné veřejnosti. Kromě editora Chemical Reviews je profesor Michl členem edičních rad a poradních rad nejvýznamnějších světových časopisů v oblasti chemie, včetně Accounts of Chemical Research, Journal of the American Chemical Society nebo Chemistry European Journal. Josef Michl je také prezidentem The International Academy of Quantum Molecular Science a členem US National Academy of Sciences, The American Academy of Arts and Sciences a čestným členem České učené společnosti. Z desítek ocenění lze jmenovat James Fleck Norris ACS Award, Humboldt Senior US Scientist, Japan Society for Promotion of Science, Inter-American Photochemical Society and Wichtel Awards, Schrödinger Medal, Porter Medal, Hayrovsky and Charles University Gold Medals, Patria Award, Marina Smith Award of the University of Colorado. Josef Michl je autorem nebo spoluautorem 5 knih o fotochemii a polarizační spektroskopii a více než 600 publikací, které získaly více jak 22 000 citací. Za zmínku stojí skutečnost, že kromě prací v časopisech ACS publikoval své výsledky například v časopise Science nebo Angewandte Chemie. A pozoruhodné je, že téměř 40 jeho prací bylo citováno více než 100krát. Jeho výzkumná práce je zaměřena především do oblasti fotochemie, solárních cel, molekulárních rotorů a molekulárních obvodů založených na organických, organokovových a anorganických strukturách, radikálových polymerací uhlovodíků a nových struktur vycházejících z chemie boru, křemíku, fluoru a litia. Vážené dámy a pánové, jsem velmi potěšen, že právě profesor Michl zahájí sérii RCPTM Honorary Lectures a ještě předtím převezme z rukou rektora Univerzity Palackého v Olomouci, profesora Mašláně, pamětní medaili Univerzity Palackého.
I'd like to start by thanking for the invitation to Palacký University. This is not my first time here. I enjoyed my previous visits and I'm enjoying tremendously the current visit. It is very nice to see how the city is developing and prospering, and the university too, and the center that I was introduced to this morning as well. So I'm very thankful, very grateful for the invitation. I'm particularly grateful for the honor of receiving from the president of the university an honorary medal. I'll try to deserve it during this presentation, but I doubt that I can. It's really quite an honor. The subject that has been selected from the few that I proposed is alkylation of gold surfaces. That is not a finished project. It's a project that we started relatively recently, and we have not yet figured out what is really going on. In a way, it is best to give lectures about subjects that are not closed, because at least I think that it is then possible to bring closer to the audience the thought processes that go into the development of a new subject. So let me get going with the alkylation of gold surfaces. The people who did the work are listed on the first transparency. The people who did the work are mostly at the Institute for Organic Chemistry and Biochemistry in Davice in Prague. And the work there was supported by the European Research Council and by the Grant Agency of the Czech Republic. But we also have collaborators who do XPS. That's a form of spectroscopy that's very helpful in our work. And they are Zdeněk Bastl at the Hejrovský Institute, also in Prague, and Frank Scholz and Florian von Brochem in the Research Institute of the Sony company in Stuttgart in Germany. So this is then the subject. How did we come up with the idea that gold surfaces might be alkylated? Well, first of all, I should say that the attachment of alkyl groups to the surfaces of gold, silver, copper, and similar metals is not new. Many organic molecules have been attached to these surfaces through sulfur. People can take a thiol. Sulfur has large affinity to the surface of these metals and will attach. And these layers were first prepared back in the 1950s. Michael Dewar was the one who started with it. Then toward the end of last century, they were popularized by many other workers, people like Nuzo and Whitesides. And today, there must be thousands of papers dealing with the subject. The modification of the surface of a metal that's possible in this way is very important in many different areas, and I will not take the time to list them. Let me just say that there is a lot of interest in this. And so you might ask, why do we need another method for the attachment of alkyls? Thank you. Děkuju.
Do you need to switch the slides?
No, that's fine. I will not switch the slides. I'll just keep this slide the whole time. Yes, why would one want another method? Well, the monolayers that are formed with thiols have many good properties. The formation is easy. You just dip a gold surface into a dilute solution of the thiol in ethanol or some other solvent, and after some minutes or hours, you have a nice layer. But they also have some disadvantages. The sulfur in these surface layers is fairly easily oxidized through air, but particularly with ozone, which is present in small concentrations in modern laboratories because of the lighting that we use in the laboratories. So they have never really found industrial use because they're just not considered to be stable enough. Also, the sulfur atom acts as an insulator. When you try to conduct electrons, metal electrons, from the gold into the organic molecules that you have attached, the sulfur acts as a big resistor. And so the notion of attaching alkyls directly to a gold surface through carbon without the intermediacy of some other atom is attractive. So how did we come up with the notion that it might be possible to attach organic groups directly to gold. We were working on molecular rotors. Here is a couple of examples of these molecular rotors. These are molecules that we attach to surfaces, such as gold, and they consist of a couple of stands, one on the left, one on the right, and that the stands hold an axle well above the surface. The bottom of the stand is mounted on the surface. The axle is here, and it carries a transverse dipole. For comparison, we also use some rotors that don't have a dipole. And then we can use electric field applied from the outside from an STM tip to cause the rotor, this part of the molecule, to turn. And we can have a lot of fun with looking at the rotation of the dipole and things like that. And this work continues, but this is not the subject of today's talk. What I want to focus on here is the fact that the way in which we decided to attach the stands firmly to the gold surface was to attach these substituent X. And as you can see, we chose substituents that had a lot of sulfur in them because we knew that sulfur likes gold and we thought they would hold well. But then we discovered that we don't need any sulfur. If we just have mercury and trifluoroacetate, the molecules, the rotor molecules, stick to the gold surface just as nicely. And so in these papers we described that. And this discovery that somehow we can use a metal such as mercury to hold a molecule to the gold surface was something that stuck in our mind. And then as time went on, we said, well, okay, let's take a look at it and see what we can do with it. So these materials adsorb on gold, and the trifluoroacetate anion is actually lost from the process. So we just have the mercuries then and nothing else that sticks to gold. Well, so we decided to take a look at mercury compounds that contain alkyls, a long one, C18, or a short one, C4, attached to a mercury on one side and a leaving group, tosylate, on the other side. And the results were already published, and I'm not going to describe them in very great detail, but I'll say enough about them to describe what the results look like. So the way to measure the amount of material that has been adsorbed on the surface in a solution in which the gold surface has been dipped is to look, the simplest one is to look at the ellipsometric thickness. And by ellipsometry, you can measure the thickness of material that you have added to that surface. And as shown here, it develops in time, 50 minutes, 100 minutes, 200 minutes, and so on. And the thickness increases. For comparison, let me show you what you see with the classical thiol, the alkane thiol derivative. And I have it here twice on two surfaces of gold that were cleaned in different ways. And as you can see, you rapidly get a thickness of about 20 angstrom, more or less regardless of the way in which you cleaned the gold. And this is well known. That's the standard procedure for putting a monolayer on gold. The self-assembly of the monolayer is self-limiting. Once the monolayer is present, the gold is covered, there is no further growth in the thickness. Well, the same is true when we use one of these mercury compounds. This is the C18 compound. And again, I have the results twice for the two methods of cleaning gold surface. You get to a limiting value. In this case, it's 13 angstrom, and then the growth stops. So now you have the organic layer attached to the surface of gold. The thickness is considerably smaller, although the length of the alkane chain is the same in both instances. You can also look at the contact angle of water on the gold surface. On a completely pure gold, that angle is small, and a drop of water looks like this on gold. This is after the gold has been cleaned with a hydrogen flame. For a layer of material that has been attached to the gold, the contact angle changes because the affinity for water changes, and depending on what it is that's on the gold surface, you can get different values. So for the layer of alkane thiol, which is a very compact layer of nicely arranged and compacted alkane layers, it's quite hydrophobic, you get an angle on the order of 110 or so degrees. This is what the drop of water looks like on a surface of that kind. Depending on how you clean the gold, you get values that are somewhat different. And the ones that we get for the compound that we use here with the mercury are sort of comparable with what we had over there. So again, that shows that the monolayer has been formed. Now, what does that monolayer look like? You can take infrared spectra of the surface. They are shown here for the CH stretching region. Here are the assignments of the various vibrations that you see there. And you can see that the spectra that you obtained with the classical alkane thiol, that would be the black line and the red line, again on the two different surfaces of gold differently cleaned, looks like this. And the ones that you get from the mercury compounds looks almost the same. Not quite the same. There is a shift of this peak as shown here. And it's already known that such a shift can also be induced in the classical monolayers by heating. And it corresponds to introduction of a disorder into the layer. So the layer that is originally formed from the alkane thiol has all the alkane chains nicely in all anti-conformations, nicely packed, nicely arranged. Ours are clearly disordered because that's what this shift tells us. Now, it seems that the reduced thickness of the layer, we only see 13 angstrom against 21, may be related to the disorder. We can also take a look at XPS. X-ray photoelectron spectroscopy is a method that can detect the elemental composition of the surface of a material. In that method, one sends an energetic photon, X-ray photon, to the surface. The photon is absorbed. Its energy is used to eject an electron. Depending on how firmly that electron was bound in the inner shells of the surface atom, it has a smaller or larger amount of kinetic energy with which it leaves the surface. That energy is measured, and from that, the binding energy of the electron in the inner shell of that atom can be determined. And from that, you can tell what the elements are that are present on the surface. Well, here is such an XPS, X-ray photoelectron spectrum. And what I show here is that there are signals that correspond to gold. Of course, that's no surprise because that's the surface that we are looking at. But in addition to the gold signals, one can also see signals from carbon, indicating that, yes, indeed, the alkyl is now sitting on the surface. And one sees signals from mercury, this one, that one. They correspond to the different energies of the electron in the inner shells of a mercury atom. But you do not see any sulfur signals, and you do not see any signals that would indicate that the tosyl group is still present. So the tosyl group has left during the process of monolayer formation, just like the groups on mercury left in the slide that I showed you first. So this indicates that the material indeed has formed a layer. The alkyls are on the surface. The question now is, what happened to the mercury? In which form is it present on the surface? The numbers that you can measure, the exact values here for the position of the peaks that are due to mercury, actually tell us that the mercury is present in its elemental form. It's mercury 0. And that is interesting. It would be unlikely that the alkyl is still attached to the mercury and the mercury to the gold, and that we would have no shift in the spectrum. So is the mercury indeed present in its elemental form, and is the alkyl then directly attached to the gold surface? You can look at that in another way, and that is by electrochemistry. You can detect the presence of mercury on the surface by doing phase-sensitive alternating current polarography. What I show here are the polarographic curves obtained initially, and then after half an hour and 1 hour of having the electrode, gold electrode, dipped in acetonitrile solution of our mercury derivative. And at first, the monolayer forms, and we see that during the formation of the monolayer, the signal of elemental mercury, the anodic oxidation of elemental mercury, actually appears, and then it gradually disappears. What happens is that the mercury that was initially formed during the deposition of the material of the alkyls on the surface is oxidized. It goes into solution, and so it disappears. So we have now an interesting result in that we can tell, yes, elemental mercury was formed on the surface, alkyls were deposited on the surface. We can remove the mercury by anodic stripping, by anodic oxidation. Well, it turns out that you can follow this process by XPS. And you can see that initially, before the anodic stripping, you had the red line showing the peaks, characteristic peaks of mercury in XPS. But after the stripping, it's all gone. And yet, at the same time, the peak of carbons, which come from the alkyls that were also deposited initially, stays. And so the mercury is not essential for keeping the alkyls attached to the gold. The mercury can be removed, the alkyls stay there. From that, you can conclude that the alkyls must be attached directly to the gold, not through the mercury. One can also evaluate the XPS in a more quantitative fashion, and one comes to the same conclusion. I show here what one finds in the initial stage and after the anodic stripping. One sees initially some ratio of mercury atoms to gold atoms in the sample. And that goes to 0 after the stripping because there are no more mercury atoms. The ratio of carbon to gold remains constant. Within the experimental error, it is not affected. The value of the footprint, or the size of the footprint that the mercury has on the surface is 13 angstrom square. That's quite a bit of mercury, because if you take the classical case of those alkane thiol chains, they each demand something like 20 or 22 square angstrom per chain. And so there is actually a lot more mercury than you could pack chains. The area per mercury atom, of course, disappears once there is no mercury left. At the same time, the area per alkyl chain, which was 36 to start with, does not change. And so the alkyls remain attached in the same way. They don't get lost during the anodic oxidation. This area is substantially larger than the closest packing area that's known from alkane thiols. And that tells us that the density of coverage of the alkyl chains on the surface is actually smaller than it is in the case of alkane thiols. Well, and that would be compatible with the observation that the thickness of our layer is only 13 angstrom, where for the alkane thiol of the same alkyl, C18, it was 21. Of course, our layer would be thinner already because there is no intermediary. We don't have a sulfur atom. So the distance from the last carbon to the sulfur and the distance from the sulfur to the gold is gone. Instead, we have just the distance from the last carbon atom directly to the gold. And so we would expect a lower value for the thickness in any case. But the difference is bigger than just that, and it apparently has to do with the fact that we have a lower density of occupation of the surface by alkyl chains, and there is also correlation with the fact that we see some gauche links in the infrared spectra. It's not all anti. The angle of inclination is probably larger also. Now, the values for the position of the peaks of mercury, as I said before, correspond exactly to those of elemental mercury, and the values for carbon are unexceptional. It is possible to remove the mercury in another way. Instead of doing the anodic splitting, you can simply heat the sample. The elemental mercury disappears. It's stable at room temperature, up to about 60 degrees centigrade. But at 90 degrees, the signal is disappearing pretty rapidly. And after 120 degrees or so, you don't see any signals for mercury at all. We do not know how much of the mercury just amalgamates inside the gold and disappears from the surface, and how much of it possibly evaporates, because this experiment, the heating, is done in vacuum. So there are two ways to produce alkylated gold surfaces, alkylated with C18, that carry nothing but the alkyls. It turns out that these films are actually thermally sturdier than the films that are made ordinarily with alkane thiols. With regard to stability to chemical reagents, solvents, oxidants, reductants, they are competitive with the alkane thion layers. They are harder to oxidize, but there are some other solvents that remove them more easily. Well, we thought this was interesting, but probably not terribly useful. If these monolayers are to be used, say, in practice, industrially maybe, people will not like working with mercury. Mercury is poisonous. In very small amounts, the ones that we use for these experiments, you might say that does not matter. But somebody has to prepare the compounds that are to be used for the experiments. And that has to be done carefully, and it is just not very practical. So we thought perhaps other main group elements might behave in a similar fashion. And we tried tin and germanium and silicon. Well, with tin, we had immediate success. This work has also been published. I show here a group of 9 compounds that were used. They're all stannanes. They contain 3 alkyls on the tin atom, 3 long chains, C18s, or 2 long chains and a methyl, or 2 methyls and 1 long chain. And they also contain a leaving group, triflate, trifluoroacetate, or tosylate. And all of these form stable monolayers from solution under ambient conditions. But the silicon and germanium analogs of these compounds do not form any such layers. We were disappointed that germanium didn't work, because even tin is fairly poisonous. It's not as bad as mercury, but it's not very healthy. Whereas germanium would be quite innocent. Well, what are the properties of the layers that are formed from the stannanes? The first thing that you notice is that the ellipsometric thickness, which again is here for the alkane thiol, the standard 22 angstrom, is now quite a bit lower. It's only 6 or 7 angstrom, and it's independent within the experimental error of the choice of the compound, of the choice of the leaving group, or the choice of the number of long chains that are attached to the tin. So all of these monolayers seem to be identical. When you look at the infrared spectra, they're also all identical. This one is different, but that's because this one is from the thiol. That's the classical comparison. All of these others are, again, identical and disordered. So it seems somewhat surprising. You would think that if you were attaching these groups through the tin atom, then it would matter for the density of the, for the number of the alkyl groups that you put in and the thickness of the layer that results, whether you have 1 or 2 or 3 of the long chains on the tin, but it doesn't matter. So once again, this suggests that we're actually transferring these long groups from the tin to the gold surface. But of course, it doesn't prove it. We can look at the XPS and ask, what is the fate of the tin? Here I have, for one of the compounds, the XPS of the neat compound itself, and that one shows all the elements that are in the molecule. It sees the fluorine and the sulfur from the triflate, and it shows the tin here, for example, and of course it also shows the carbon. The monolayer on the surface does not have any of the fluorine, and it does not have any of the sulfur. Once again, that leaving group is gone. It does contain tin, however, and we can ask, what is the form of tin? Well, that corresponds to a tin oxide. And it is difficult to tell from XPS shifts whether it's tin monoxide or tin dioxide. And it's likely, since we work under ambient conditions, that the oxygen comes from the atmosphere. So perhaps originally tin was also formed as tin zero, just like mercury was, but it got oxidized by the atmosphere. Now, encouraged by this, we thought, well, perhaps we can figure out what alkyls can be and which ones cannot be transferred from the tin atom onto the gold surface. It was quite clear that there is some differentiation between the C18 that was transferring nicely and the methyl that didn't seem to. And I have here a collection of results for a variety of stannanes. And these results show the ellipsometric thickness. And once again, I have here for comparison the result for the octadecane thiol that gives us the thickness of 22. And then I have a series of compounds that have alkyls of different lengths. In order to be sure that we are looking at alkyls that are transferred to the gold from the tin and not just from some impurity floating in the atmosphere or in the solution, we frequently use deuteriated alkyls. Now, if you use deuteriated tetramethyl tin, you find that there is actually no layer formed. A thickness of 1.5 angstrom is basically within the accuracy of the method equal to 0. We are not making any transfers. So the methyls don't transfer. Interestingly, ethyls don't transfer either. We still get this very low value. If we go to a propyl, that's here, we can see that 3.6, a very thin layer. And then we can go to a series of butyls. All of these contain butyls. And all of them transfer quite nicely, except for this one. The trifluorinated, terminally trifluorinated butyl does not transfer at all. But the others all give the same result. So it seems that they are 5.6, regardless of what particular butylated stannane we use. Once again, that suggests that we are transferring just the long alkyl and nothing else from the tin to the gold directly. Here are contact angles, and they fit very nicely with the results for the ellipsometric thickness. The contact angle of cleaned gold is about 55 or 60. The value 20 I gave you before is something you can only get in ultra-high vacuum. Once you take a gold surface into the atmosphere, even just for a few seconds, it will become much less hydrophilic. So the C1 and C2, the methyls and the ethyls, give pretty much the same result as nothing at all. The trifluorinated butyl also Here is the propyl that gives a somewhat higher contact angle, and here are all of the butyls other than the trifluorinated one, and they seem to give the same result. So we seem to be transferring the butyl to the surface of the gold, but not methyl and not ethyl. Why would that be? Ordinarily, in organometallic chemistry, methyl shifts are much easier than shifts of higher alkyls. But here it seems to be the opposite. If you look at infrared spectra, you find again that it does not really matter what source of the butyls you take, you get the same IR spectrum. It makes no difference whether there are 4 butyls on a tin, or 2 butyls on a tin with 2 tosylates, 2 butyls with 2 methyls, and it makes no difference whether the methyls are deuterated or not. And we do not transfer any of the deuterated methyls. We would see that in the infrared in a different area. And that is illustrated on this transparency here. When you take a compound that is completely deuterated, 4 times butyl that has no hydrogens, well then you get a spectrum that's shown in the blue. It has CD stretches, but it does not have any CH stretches. You might think that this is a trivial experiment that provides no information because there are no CH groups in the alkyls on the tin, but it is an important experiment because it tells us that we are not incorporating any impurities from our solvent or from the atmosphere. If you use a compound with ordinary butyls or a compound with ordinary butyls and deuterated methyls, you get the spectra shown here in red and in green, and those show the expected CH stretches and nothing at all in the CD range. Well, this tells you that the methyl groups do not transfer. Here are the conclusions from a large number of measurements that were made for all of these compounds. And I have pretty much told you what these conclusions are, so I will just go over it very briefly. We do not transfer methyls. We do not transfer ethyls. We do transfer propyls. And we transfer butyls, except for this one, the one with the CF3 group. We do not transfer any of the tosylates. They don't stay there. They leave, whether we have 1 or 2 on the molecule. If we look at XPS, we see again pretty much what we expect. You can see that the tosylate is not present. You can see that butyls are present. And you can see the tin. But the tin is in an oxidation state of +2 or +4 as an oxide. Now here comes a surprise. The tin is absent when we deposit the butyls from this compound. It is present when we do it from that compound. You can see the tin peaks here, but you don't see them there. So this is an example that again shows that the alkyls are not attached to the gold surface through the tin, because even in the case in which there is no tin, the peaks are gone, this peak is gone, the alkyls still stick. The alkyls are there. The tin did not stay this time. So we have a way to get purely alkylated gold surfaces without any additional impurities, such as a metal, tin, even in the case of in which we use the stannanes. Now, I've been indicating all along that these layers are disordered and thinner and less densely packed. That should be apparent in their permeability. And sure enough, if you look at the electrode behavior of a gold surface that has been covered with one of our films, it does not really, the film does not really block the electrode very well. It reduces the cyclic vontometry peaks, the anodic and cathodic peaks, for a standard. This was done with ferricyanide. The ferricyanide is still oxidized and reduced. Not as much as on a clean gold surface, but not much less. These peaks are reduced only slightly. If you looked at the octadecane thiol film, then you would have no peaks here at all. One can detect the blocking using the impedance spectra, which are shown here. This is pure gold surface, and you can see that the filmed surfaces are different, and the most blocking is observed for the densest film. That's the one in which we leave no tin on the surface. So these layers are permeable, but they do cover the gold particles. That may be considered a big disadvantage. What good is a coating if it doesn't really cover and protect the surface? But every cloud has a silver lining. You could say, well, suppose I use nanoparticles of gold. Maybe I use clusters of gold. They have catalytic properties. They can be used for catalyzing oxidation and many other reactions. But they tend to aggregate if I don't protect them. So perhaps if I could coat my gold clusters or nanoparticles with a permeable layer, it would still be good enough to prevent aggregation of the particles and precipitation, and yet allow access to reagents to reach the surface of the catalyst and to diffuse out again. And so we are pursuing now the possibility that these films might actually turn out to be useful for gold catalysis. What I show here is relevant for that application, namely what is the chemical stability of our films. The stability was measured on the flat surfaces and is indicated here for a variety of chemical reagents, acids and bases and oxidants and reductants. And what I show is the reduction of the IR intensity that we observe after 18 hours, that's in cyan, and after 44 hours in gray, of immersion in that chemical reagent. And you can see that some of the layer disappears, but not all of it by any means, and much of it still stays. And so the chemical stability seems to be roughly comparable to what one knows already from the alkane thiols. This is thermodegradation. After 1 hour at 20 degrees, there's no change. At 80 degrees centigrade, you lose 20% of the IR intensity. At 140, you lose more. But even at 200, after an hour at 200 degrees, you still have quite a bit of the material left. This thermostability is much better than what one knows from the standard alkane thiols. Well, so let's pursue a little bit this notion that perhaps one could use these permeable layers for catalysis. We have used the laser ablation procedure to prepare nanoparticles of gold. I indicate here approximately how the experiment is done. There's a gold plate in a solution. We've tried something like 30 different solvents and then picked the best ones. And here are TM images of the nanoparticles that result in ethanol, or you do the ablation in THF. And these are the conditions of the laser conditions that were used. Now, if you take these particles, you can then treat them with alkane thiols. Of course, people have done that before, but also with these alkyl stannanes. And what do you see when you take the NMR of the resulting solutions of nanoparticles? Well, I have here a comparison of what happens for the alkane thiol. This is the spectrum of the free ligand, NMR in acetone. It's deuterated acetone, actually. And here, what you see on the nanoparticles. And in the nanoparticles, you see both the CH2 groups and the CH3 group in the alkane. And down here, in deuterated chloroform, you have the similar results obtained when you use this alkylated stannane for the same experiment. And once again, we see the CH3 group and we see the CH2 groups. We also see some others that we have not yet assigned. This is fairly recent, and that may result from some solvent decomposition during the ablation process. and that we'll be able to do experiments in which we can look at reagents coming to the gold surface through these permeable layers and taking a look at chemical transformations that result. Now, none of this actually tells us what the real mode of attachment of the alkyl is to that gold surface. Is it attached by having a bond from the CH2 group at the end of the alkyl to a gold atom, or to 2 gold atoms, or 3 gold atoms? Or have we perhaps lost a hydrogen, or 2, or 3, or 4 from the end of the alkyl chain? And is it now attached from a CH group, or maybe just a C atom, to some number of gold atoms? Or do we now have a double bond or a triple bond at the end of the alkyl? And are those attached to the gold surface? We do not know yet. So this is a big issue and the next problem to address in this ongoing project. One of the methods to answer that question is to try calculations. And we have the first results of calculations here. This is with a semi-empirical method, a relatively simple-minded way to describe gold and its adsorbates. And it shows what you get from geometry optimization, including the bond lengths, the CC bond lengths and the C gold bond length. If you assume a rigid structure for the cluster, we have simply taken the known structure of the cluster AU55 and cut it in half and used that. Or if you allow the gold to relax. If you allow the gold to relax, as you can see, the mode of attachment of the CH2 group changes. And so this is to be pursued. We need to do many more attempts starting from other geometries, and we also want to use a DFT procedure to verify the correctness of this. But most important, of course, we also want to do experiments. So we have synthesized already a series of butyl stannanes in which only one CH2 group is labeled CD2. And it could be the last one and the next one or the one after that. And we hope that from a combination of spectroscopies, we'll be able to tell a little more about how the alkane chain is actually attached to the gold surface. And then will come the next question, which is, what is the mechanism? How does the alkyl slide from its tin atom onto the gold surface? As for that, we don't have any ideas yet. So clearly, this is not a finished project, and it's a fascinating project to me in that it's entirely new chemistry. I don't think that anybody would have guessed that you can transfer alkyls from mercury or from tin onto a gold surface. Although I must add that in the recent past, in just the last few years, a group at Columbia, Venkataraman, Breslow, and their collaborators, have measured conductivity through alkane chains using stannanes to attach their chains to a gold surface. This was an independent discovery. They were not aware of our publication on this. And they believe that the CH2 is attached by a single bond to a gold atom. Maybe they are right, but maybe not. This is a big open question. Whether this can be used ultimately to attach our molecular rotors to gold is a hope, but we cannot say for sure. There would be advantages to attaching molecules not through sulfur, not through thiols, but from stannanes, because the stannane is chemically much more inert than a thiol. If you want to do chemical transformations, synthetic transformations on a molecule that has a SH group, even if you protect it with an acetyl or some other group like that, it's difficult. The sulfur tends to react with all sorts of things. It will tend to ligate to metals, it will be oxidized, and so on and so forth. Whereas the stannane is much more inert, and it would be an advantage when we elaborate fairly complicated molecules like the ones that you saw on the first transparency and try to attach them to a gold surface for whatever reason. So to summarize then, we find that N-alkyls that are longer than ethyl are transferred from tin and from mercury to the surface gold atoms from solution under ambient conditions. The detailed nature of the resulting attachment and the mechanism are unknown at this time. The resulting self-limiting monolayers are similar to those that are well known from thiols, but their stability is similar, but are less ordered, less densely packed, and more permeable. That might be advantage in some applications, disadvantage in others. The tin is left on the surface in the form of an oxide. In one case, no tin is left on the alkylated surface. Mercury is left as elemental mercury, and it can be removed by heat or by anodic oxidation without disturbing the alkyl layer. The alkyl germanes and silanes don't deposit monolayers under these conditions. But we have tried some other elements, and it seems that aluminum and bismuth can both be used to deposit alkyl layers on a gold surface. Well, this is an unfinished story. I would welcome questions and suggestions about what we really ought to be doing next. Thank you very much for your kind attention, and thank you for the invitation.